Thank you. Thank you very much for the invitation. Yeah, so I'll talk about torsion homology growth. And so I'll first survey some more or less classical things. And in the end, I'll briefly talk about something new, which is very much work in progress. And it's with Kevin Lee, who's here, Marco Moraschini, and Roman Sauer. Okay, so but I'll start very gently with a general overview. So I first talk about gradient invariance of groups. And yeah, let me just make a definition. So if alpha is some invariance on groups, and it's supposed to give you a number, it's a very crude thing. It's just for every group, it will spit out a number. And I want this to be an isomorphism invariant. So if you have isomorphic groups, then you get the same number. Okay, so this is an isomorphism invariant. Okay, if you have that, then, well, you can turn this into something else. Namely, you could look at residually finite groups. And then you could do the following. So if, let's say, gamma is an infinite residually finite group. And now you could look at a residual chain inside of gamma. So it's a nested sequence of finite index normal subgroups of gamma whose intersection is trivial. And in principle, you could do it for more general systems, right? You could look at more general directed systems, but for simplicity, let's just stick with this standard situation that you have such a residual chain. And then what you can do, well, for each of the members in this chain, you can evaluate alpha on that. Right, so but now this is a finite index subgroup, so maybe you want to normalize by the index. Okay, and then now you optimize in some way, and there are different choices, but for today, let's just take the limit superior over all these values. And then you get something, again, a number. And of course, if you have no further conditions, then it might very well be infinite. Okay, so this is a general procedure that you can do. So it's basically looking at your residually finite groups through the lens of its finite index subgroups. Yeah, so let's do some examples. From isomorphism classes of groups to numbers. So it's no, any group. Like, and of course, the interesting case is that you have some residually finite group. And of course, later, if you want to have reasonable values, then you might have finiteness conditions on your group. Like, I don't know, you have a finite classifying space or something like that. But I mean, you can write this down, and this generality, of course, in general will be meaningless. Okay, so let's do some basic examples. Okay, so what could you do? You could take some natural number, and you could take a coefficient field. And then what you get is you get a Betti number gradient. And I'll denote this by BK hat, and in this case with coefficients in F. So this is a Betti gradient over F. Okay, so this is a very natural thing that you can do. Another thing that you could do is you could take the minimal number of generators. And then you would end up with the rank gradient. And I'll denote this by RG, rank gradient of the group. And then the thing that will keep us busy today is you could take the log of the number of the torsion elements in homology with integer coefficients. And then the corresponding gradient, I will denote this by TK hat. And then this is the log tor gradient. Okay, so these are some obvious examples that you could use. Of course, I mean, you can also, similarly, you can do this for spaces and finite coverings, and then you might have also additional ideas of what you could use. Okay, so yeah, so the very general question is, of course, I mean, there are many questions. So for example, you might wonder, does this depend on the chain? And if so, how? Right. And then, of course, it's a related question is like, how can you compute this? And well, I mean, computing things usually means that you have to understand what kind of inheritance or divide and conquer things you have. So more or less the same as looking at inheritance properties. And then, of course, you might also wonder what's the meaning of all this. Maybe I'll come back to that later. But so the general idea that I want to convey today is that well, dynamical systems can contribute to that. And there are classical examples where this works quite well. And then we'll discuss a bit what to do about the case of logarithmic torsion. Okay, so let me give you a theorem. And well, there are many people that contributed, and I will list them when I make precise statements. So yeah, let's assume we have such an infinite residually finite group. And let's assume that we have a residual chain. And now, in order to get something reasonable, we should also assume that gamma satisfies some finiteness conditions. So for simplicity, I'll just say that gamma have a finite model for the classifying space. Yeah, you can improve on that, but let's ignore this. Yeah. Okay, so then we have the following statements. So first, in every degree, maybe let's start with the Betti gradients. So with the Betti gradient of gamma with respect to this family. And now we should restrict to rational coefficients. So but then you can express this very nicely. Namely, what you can do is you can express this as a completely, like in a different way, in a global way. Namely, this is the case L2 Betti number of gamma. And that's the Löh approximation theorem. Tells you this. Okay, so this object here, this L2 Betti number of gamma, as I said, this has a global definition, and you can define this. Yeah, you can say this is equivariant topology or homological algebra or analysis. So this has several different descriptions. So in this case, this gradient has an actual meaning, okay? And it's this thing. Okay, but it gets even better. So you can, once you have this description, then you can, yeah, translate it into a different setting. Namely, you could say, well, if I have my group and I have such a residual chain, then I can look at the corresponding inverse limit, and I'll denote this by gamma star hat. So this is just the inverse limit of all these quotients. These quotients are finite things, right? And because these things are nested, you can go between them. And okay, so first you can consider this as a set, but then also, of course, gamma will act on this by translation. And then you could say, for example, you put the finite counting measures on these things. And if you do it right, then also on this inverse limit, you get you get a measure, finite measure, normalize it to be a probability measure, and then you have a probability measure preserving action. And if gamma star would not be a residual chain, but let's say the family of all finite index norm subgroups, then you would just get the pro-finite completion of gamma. So this is also why I use this notation. Okay, so this is a dynamical system. And if you have such a dynamical system, then you have an orbit relation. It's just the orbit relation given by this thing acting on this probability space. And then Gaboriau found a way to formulate what L2-Betty numbers are of such equivalence relations. And then you can write this as the L2-Betty number of this dynamical system. This is a result by Gaboriau. But then you can move even further, and then you can say, oh, maybe in this case, this dynamical system, there's nothing special about this for this context, because you can just use any dynamical system. So as long as it's essentially free probability measure preserving. By Gaboriau. Okay, so what you see in this case of the basic gradient over Q, you really have this very perfect correspondence. You have the chains, you can make this ad hoc definition of the gradient, and then you have a global description in classical equivariant terms, and you also have this dynamical description. And so the dynamical system does not matter. In particular, this thing here is independent of the residual chain that we started with. Okay, so it's a little miracle. Okay, so I emphasize that you should use Q here, because if you, for example, you could say, oh, I take finite field coefficient, and then somehow the situation is much more mysterious, and it's not clear what you should put on the right-hand side. Okay, so that's nice. Then maybe let's move on to the rank gradient. And for the rank gradient, you get that this can be also expressed in dynamical terms. So basically, there is a dynamical version of minimal number of generators, and that's cost. So you can look at the cost, again, of this dynamical system that we have here, and then you have to renormalize by taking -1. And this is a result by Albert and Nikolov. Okay, so again, you have an expression in terms of dynamical system, but it's not clear how this depends on the chain or on the system. So this is the dependence, like independence of residual chains. Right here we have it, but here it's unclear. And it's maybe doubtful whether it should be independent or not. Okay, and then of course the obvious question is like what to do about the log Tor gradients. Yeah? Okay, so maybe if we go back to the L2-Betty number or Betty number case, so there's there are the L2-Betty numbers that somehow make this translation work, and now that there's an obvious candidate, basically, for this log torsion thing, and the natural candidate is something like the L2 torsion. Now you have to be careful to make this into a reasonable statement. So I put it in quotes, or more generally, the Fugler-Cadison determinants. Okay, but so it's wide open what the exact relation is. So in some situations, some things are known, but it's really this torsion gradient is very hard to compute or estimate. So let's say this is more difficult than the Betty gradient. And the reason is basically that if you talk about these torsion things, and I'll get back to that later, I mean, sooner or later, you will have to talk about truncated determinants. So somehow it's unavoidable. And determinants are just much harder than traces and dimensions. Okay, so you cannot expect too much. Yeah, so then maybe you might wonder, okay, why go through all this pain? Why should one be interested in this? And so, okay, there are different reasons why one might be interested. So first of all, I think it's a very natural thing to consider. Looking at these residual chains and looking at invariants and see what happens, understanding this. But also there are like number theoretic reasons, but because I'm not a number theorist, I cannot really comment on the details. But so there are lots of people that are trying to understand in detail what happens for, let's say, arithmetic, hyperbolic free manifolds. And also, if you somehow generalize the setup a little bit and talk about more general things, so you will also automatically fall into the world of number theory. So for example, similar questions are related to the Mahler measure of integer polynomials and then also to the lemma conjecture. So it's, yeah, so there are good reasons to expect that this might be difficult. And of course, like the art is to find a way to bypass these difficulties and still make reasonable statements. Okay, so yeah, let me quickly say something about how in principle or one gets a bounds for the logarithmic torsion. And usually we just, I mean, the easiest case is to find bounds from above. So okay, so the idea, of course, is the following. I mean, this is a homological thing, so maybe we should start thinking about chain complexes. So let's say that C star is a chain complex. And let's say over the integers, right? And then the idea should be that if this is small, yeah, then also the logarithmic torsion should be small. Okay, so something like this should be true, but maybe we have to be a little bit careful. So let's have a quick look. So if you look at your chain complex, okay, then of course the kth homology, we all know what it is, but let me write it down anyway. So it's the kernel of dk modulo the image of dk plus 1. Okay, so if you're just interested in ranks and stuff, then okay, it's more or less okay to understand a lot about the kernel of dk and then you're fine. But if you're interested in torsion, then somehow this image of the boundary operated from 1 degree above, that might generate a lot of torsion, right? Large torsion with few generators. No? Okay, so what you have to do whenever you want to have a statement like that, you should control the rank of the kernel, or maybe let's be a little bit fuzzy and just say we just take the rank of ck. Okay, so that's a very crude estimate, but good enough in many cases. But we also need to know something about this boundary operator. And there is a basic statement of this type that makes it work. And yeah, I just give one formulation. There are lots of different variations of this, but like the core of it is always the same. And I think it's attributed to Gaber. Maybe not exactly in this form. Okay, so if C star is a chain complex over Z, and let's say it's a finite type, it's finitely generated in every step, and maybe also let's say it consists of 3 things, so consisting of finitely generated 3 modules. then if you want to bound the logarithmic torsion of hk of c, well, then you can do this by taking rank of ck times the logarithm of the operator norm of the boundary operator. And now this operator norms, I mean, if these finally generated free modules, and maybe you want to pick bases beforehand, and then you take this this norm with respect to the L2 norm. Okay, so this is one way to state this. I mean, there are more refined versions, and if you look at this, so this always basically goes through looking at determinants or at like Smith normal forms of things. Okay. Okay, so this is the basic statement, and this is what people usually use if they want to bound the logarithmic torsion group. Okay, so this has been exploited in various ways. Okay, so there are many versions of this. Let me just mention two of these things. So of course, now what you have to do is basically you have to look at your finite index subgroups, and then you have to find good chain complexes for the finite index subgroups, and then apply this estimate. Okay, and so one thing only works if you have a manifold model for the gamma. So this is very restrictive. So if there's a manifold model, the gamma. So I mean, you have an oriented close connected manifold that is a classifying space for gamma. So as I said, this is super restricted. Then Roman-Sauer used this in many ways to get good vanishing results for the logarithmic torsion growth. And maybe let's mention another thing. So there is the cheap rebuilding property technique. Okay. Yeah, so this is a topological version of finding good chain complexes, and it's I will not state it precisely because it's intricate to state. So this is by Albert Bergeron, Acek, and Gaboyo. And yeah, so what's the idea of this property? So this is a property that ensures that you get the right kind of estimates to show vanishing of logarithmic torsion growth. And in addition, I mean, that's maybe not so difficult, but what is interesting about this property, it has very good inheritance properties. So it propagates nicely, but this is also what makes the property very difficult to state. And there's a similar thing by Okun and David, which is basically in the same spirit. Okay, so okay, why did I mention this manifold case? Because this manifold case is it has the advantage that you somehow uniformly get lots of estimates all at once, but you have this big restriction. And especially for logarithmic torsion growth, it's extremely hard to move away from this using the same technique as what Roman-Sauer. Okay, so that's the rough outline how to get such bounds. And now maybe I want to return to the dynamical world. And yeah, I want to talk about a special class of groups where somehow it all works out very nicely. And I'll basically only talk about the amenable case, and then maybe I'll say something about how to get away from that. Okay, and I'll first state basically the classical version, and then I explain how you could use dynamical systems to replicate these statements and then maybe move on. Okay, so this is again a theorem by many people. So that gamma a residually finite, infinite, amenable group. And then again, we need some finiteness conditions that admits a finite model for B gamma. And we assume that we have a residual chain. Okay, then we can conclude the following. So the first one is that for all degrees and all fields, we have that the Betti number gradient is 0. Okay, so for yeah. Okay, so if F is Q, then we could just use this theorem here, and then we only need to prove that the L2 numbers of infinite amenable groups are trivial. And there are many ways of doing this. And there's one that I particularly like, namely you could go to the Gaboriau setting. And then if you know that basically for whatever infinite amenable group you take and whatever essentially free and ergodic action you take, you get the same equivalence relation. So then you only need to compute it in one single example for the integers. And then there, for example, you can do it using the Rochlin lemma that allows you to subdivide measure spaces. So there are lots of ways of proving this, but maybe I'll also say what maybe the first proof is of this. And the first proof of this is by Chiga and Gromov. I mean, they don't state it for all fields, but it just works. Okay? And how do you do this? Well, you take the right type of Fellner sets, of course. So you could take Fellner coset representatives in gamma. Oh, well, I mean, so if you, I mean, you can really loosen this, but well, you don't need much. I mean, in particular, if you're in this setting here, then you don't need much. I mean, if you really want to do it using these Fellner coset representatives, you need something. I mean, at least something like finite type or something. Maybe it doesn't have to be finite dimensional, but it has to be like finite in each dimension. Yeah. I mean, but yeah, there are lots of ways of relaxing this. Okay. And the second is that we can look at the rank gradient. This is 0, and I think the original, like the first proof, is by Leckenby, and it's also yeah, it's really in this residual world. But of course, you can also use the Abed-Nikolov theorem. And then you see, oh, it's the cost of this relation. And then I already told you, oh, this relation, I mean, if gamma was infinite amenable, there's, okay, it's really, you only have to look at one particular type of actions of the integers, and there you just compute it by hand. Okay, so you could also do it dynamically. And the last one is the logarithmic torsion growth. And that's due to Peter Coppola and Nikolov. And again, basically, I mean, it's combinatorics is involved, but it's basically again based on these using Fellner's coset representatives in gamma. Okay, and it's not so clear what a good dynamical proof for this would be. Okay, so if you're looking at dynamical proofs, then now there, as I said, basically there are already two techniques around, and you can do this manifold case, yeah. So if the gamma has a manifold model, then one can prove all of these all at once in one go by showing that a specific invariant of manifolds is 0, and this is let me say, so this is simplicial volume, and then there are also dynamical versions of this. Okay, and that's okay. Maybe I do not go into the details because this is like a very manifold topological thing. So this is together with Roman and several other people. So it's a long story. But what is nice is that somehow you get them all in one go. And also by now we have a toolbox that works quite well, and it heavily depends on dynamical properties. So we can go beyond this amenable case and also do some other interesting cases. But it's restricted to situations where really like everything is 0, right? You cannot do better than that. Okay, and then the second case is this like cheap rebuilding property technique. And what I want to explain now is, so we have a dynamical version of this. And yeah, I will roughly sketch how this works. Okay? And I will call this the cheap embedding property. Okay. Well, it should be called like dynamical cheap embedding property, but there are other things that will follow. So it's like it's getting longer and longer. Okay. And this is yeah, don't work with Kevin, Marco, and Roman. Okay, so I'll explain roughly how this works. Okay, and it's basically just we look at this estimate by Gabor, and we reinterpret it in a dynamical language. So, or like the cheap rebuilding property. Okay, so I'll make a definition, and it might look complicated, but the idea is very simple, okay? Okay, so let's say that gamma be a group, and for simplicity, let's say again it has a finite model of the gamma. And now we need a dynamical system. So let's say that gamma acts on some probability space, should be a standard Borel thing, but okay, it's probability measure preserving and essentially free. Okay, so this is also given. And let's say we have a natural number k, and now we want to say what it means to have the cheap embedding property in degree k. Okay, so then gamma has the cheap embedding property in degree k. And now it's with respect to this action. If the following holds, and now we just look up at this estimate by Gabor. And okay, so we can improve on that. Of course, we don't really have to estimate the homology of C, right? I mean, it suffices to write C as a homotopy retract of something that has the smallness condition. Okay, and then because then the homology of C will inject into the homology of this other thing. And if this other thing has small torsion, then also the homology of C will have small torsion. So this is sufficient to do that. And yeah, let me write it like that. So if the following holds, so now we have to say that everything will become small, right? So there will be a limiting process at some point. So for every epsilon bigger than 0, there exists. Okay, I'll just write it down and then I'll explain some more things about this. Mark projective augmented chain complex that now lives again over this equivalence relation. So if you have such an equivalence relation, then you can build something like the group ring. Well, so it will contain L-infinity functions on X with integer values, and it will contain the group elements, and it will be like a reasonable combination of both. But as the notation suggests, it will only depend on the relation. So this is like truly a dynamical thing. Okay, so in complex. Okay, so what kind of complex do we want to have? So let's call it E star, and it augments to L-infinity of X Z. So like this, these are the dynamical integers. Okay, and a Z gamma chain map from, let's say, we could take a cellular model of the cellular chain complex of some finite model of E gamma with integer coefficients. Well, now we want everything to be equivariant, so we better take E gamma instead of B gamma, so the universal covering. And the chain map should go to D star, and it should be compatible with this augmentation, extending the inclusion of the integers as constant functions into this function space. Okay, so these because we have here a model of E gamma or E gamma, so this will be a free resolution of the module Z, and then we just compare this to this other thing. Okay, so for every and then we have another condition. Of course, now this delta star D star, that should be epsilon small, such that okay, so I'll say something about this in a minute, so that the dimension of dk times the logarithm of the norm of the k+1 boundary operator is at most epsilon. And there's a technical additional condition that also the dimension of dk should be less than epsilon. So now you might be, I don't know, scared, right? Okay, epsilon is something that's very close to 0, so the dimension should be smaller than that. So maybe I should explain what such a marked projective thing is. So this, what's the advantage of this ring over the integers? It contains a lot of projections. Namely, whenever you have a measurable subset of X, let's say A, then you can look at the submodule of this ring generated by the characteristic function on A. I mean, you have to know that L-infinity X embeds into this ring, but then if this, and this is a projection. So this is a projective module, and you can give this a reasonable notion of dimension. And of course, the dimension of this thing is just the measure of the set. Okay, and in this way, you have more possibilities of finding small modules. Okay, and this is somehow why this makes sense. Okay, so that's the notion. And I admit it looks a little bit technical, but it just says that you can embed your chain complex into small chain complexes over this ring. Okay, so what's the theorem that goes with it? The theorem, of course, says that if you are in the situation, then your logarithmic torsion thing will be 0. So, okay, so if gamma, okay, admits a finite B gamma and is infinite residually finite, and we have a residual chain gamma star and gamma, and if gamma now has the cheap embedding property in degree k with respect to now, of course, the action on this limit space for this residual chain, then yeah, tk hat of gamma is 0. Okay, so that's the statement, and let me just indicate how to prove this. Okay, so the idea is very simple, but to carry it out is a true nightmare. Namely, so you have this thing that lives over this equivalence relation of n, and you have any measurable sets in there, and you have any linear maps over this thing. But I mean, if you're in the situation that you have this profinite completion thing, then you have the cylinder sets, and they are measurably dense in the sigma algebra of this thing. So you can approximate everything by these cylinder sets. And yeah, that's what you do. So approximate everything by cylinder sets in thing. So this is also what Albert and Nikolov do for the rank gradient, and this is also what happens in the simplistic volume case. So this is basically an established path to do that, but it's always very technical to carry out, because you have to all the norm bounds that you have to make everything explicit and make sure that it all carries through. And so you do that, and then you are in a better situation than before. Then there's a way, because the left-hand side is a resolution. Now you have to figure out how to change rings to a good ring. But then this means you have a projective resolution of this over this other ring, and then you get a map back for free by the fundamental lemma of homological algebra. So this will write your C thing as a retract of something that is small. Okay. Homological algebra. Get a return map. And then basically apply this estimate by Gabor, right? And now this works because now everything is in terms of these cylinder sets. And if you look at this, this just means that you're talking about finite index subgroups, properly like that. And then you can translate back to the situation that you have finally generated free things over the integers and literally use such a bound, not this bound, but something like this. Okay, and this gives the theorem. So okay, no, this is general. You can take whenever you have this, you will get this vanishing. Okay, but yeah, so amenable is a good keyword. Yeah, so because all infinite residually finite amenable all, let's remove residually finite, all infinite amenable groups, yeah, of finite type, right? We need this finiteness condition, satisfy the cheap embedding property in all degrees and with respect to all essentially free dynamical systems. Okay, so in particular, what we obtain is, that's what I said, we can replicate things. Eh? So we get a very complicated proof of this nice theorem by Clara Löh and Nikolov that the logarithmic torsion growth of an amenable group is 0. Okay, so why is it interesting anyway? So the hope is now, because this is now in a dynamical setting. This is dynamical language. You might hope that you have new inheritance properties, right? Now you can ask dynamical questions. And so this might lead to further computations, but that's what we are currently still trying to figure out. Thank you.